Welcome to Let's Get to the Marks. I'm going through A-level biology, the maths. Okay, what's this about? This is going to be one of a series of about 8 videos. I'm going to cover every single maths question that's ever been asked in the recent AQA biology specification. So let's get into it. Don't forget to like, share, subscribe, all that jazz. Right, figure 5 shows the further information about a channel formed in the cell surface membrane of the APs. Okay, we don't need to know all the bluff about the question. Let's get into the maths. So we have two alpha helix coils in a membrane, phospholipid bilayer, and we got 1.1 nanometers for the width of each coil and 4 nanometers for the width of the whole channel. Use figure 5 to calculate the cross-sectional area of the channel through which the ions can pass. Assume the cross-sectional area is circular. Use pi 3.14 in your calculation. Give your answer in nanometers squared and in bold to 1 decimal place. Make sure you highlight the key facts as I'm doing here. Pause the video, have a go, and then unpause and watch the answer. Okay, so we're assuming this is a circle, and the question is asking us to work out the area of that circle. So we only want the area of that circle. So you've got to know how do you calculate the area of a circle? Well, hopefully you know that you use pi r squared to calculate the area of a circle, right? So we just need to do pi r squared. So we need to find out the radius of that circle. Well, the diameter is going to be the full 4 nanometers, and we need to minus those alpha helix coils, which are 1.1 nanometer each. So we're going to do 4 minus 1.1 times 2, or 4 minus 1.8. Sorry, 4 minus 2.2, which equals 1.8. And we need to find the radius of that diameter, so it's only half. So we need to divide the 1.8 by 2 to get r, and r is going to be 0.9. So now all we've got to do is 3.4 times 0.9 squared, and you're going to get 2.54. Make sure you don't miss. Here I've circled 1 decimal place. So because the 4 is smaller than 5, we round down. We're rounding down to 2.5 nanometer squared. And that's your answer for 2 marks. Awesome. Let's move on to the next maths question. Okay, for this next question we have use figure 9 to calculate the percentage increase in the rate of transpiration from 1 p.m. to 2 p.m. So on the left, we've got rate of transpiration. On the right, we've got height of the tide. We don't need that. And at the bottom, we've got the time. Now, it asks us to calculate the percentage increase in the rate of transpiration. So what we need to do is, first of all, we're looking at rate of transpiration, and we're looking at the times 1 p.m. and 2 p.m. So let's locate 1 p.m. and 2 p.m. There's 1 p.m. And we can just circle this cross here. This plotted point is 1 p.m. So that's 0.75. That is our rate of transpiration at 1 p.m. Now we need to figure out the rate of transpiration. I can't even speak. Rate of transpiration at 2 p.m. And conveniently for us, it's this plot here at 0.80. So now what do we need to do? Well, percentage change or percentage increase, you just need to do the difference over the original. So it doesn't really matter whether you do 0.75 minus 0.80, whatever. We know it's a percentage increase. It tells us, so it's going to be a positive answer regardless of whether we get a negative one. So work out the difference. You can do that by going 0.8 minus 0.75 and then divide that by the original, which in this case is 0.75. So what is the percentage increase? Let's have a little look. So we've got 0.05, and we're doing that over the top of 0.75. We want to turn it into a percentage, so we need to times by 100. Now, it hasn't asked us to do it to 1 decimal place or 2 decimal places or anything like that. And I got 6.67. There we go. Okay, you can round it up, round it down, do whatever. You should always go to 2 significant figures or at least 2 decimal places. So there we go. Lovely jubbly. Let's move on. Okay, so we're looking at table 4. Use your calculated volume and surface area volume ratio to 2 significant figures. Okay, yeah, whatever. We need to fill in these blank spaces in the table. Okay, so we're looking at the healthy fish gill. We can see we've been given surface area and volume. First thing to do is calculate the surface area to volume ratio. Have a go and then unpause and watch the question. All right, well, look here. We've got the surface area to volume ratio of the damaged fish gill. And I know the volume is 1 there. So I know that in AQA, when you do surface area to volume ratio, they want the volume represented as 1. So I need to divide the volume by 2.3 times 10 to the 4, divide it by itself to get 1, and then I divide the surface area, 7.4 times 10 to the 3, by 2.3 times 10 to the 4. And so I'm going to get 0.32 to 1. So that is the surface area to volume ratio of a healthy fish gill. Now we're going to look at a damaged fish gill, and we need to find the volume this time. So we've got to rearrange the equation. What I can do here is I can see that when I did the healthy fish gill, I divided the surface area, 7.4 times 10 to the 3, by the volume. So if you make one of these magic maths triangles, the surface area must be on top and the volume underneath, and the SAV or ratio underneath as well. So now I can work out exactly what I've got to do to calculate the volume. So instead of thinking, oh, do I times them or do I divide them? Taking the guessing out, put them into an equation. Surface area divided by the volume equals the ratio. So here I want to do surface area over the ratio, and that will give me the volume. So 1.1 times 10 to the 4 is the surface area of the damaged fish gill, divided by 0.13, which is the ratio, and we're going to get a volume of 85,000. We need to put that into standard form and to two significant figures. So we're looking at 8.5 times 10 to the 4. And there we go. Wonder bar. That's the second mark. Okay, if you're liking the video so far, make sure you hit the like and all that jazz. So in your calculator, you would have got 84615. The fact that the 6 is bigger, you round up. All right, for this next question, table 1 shows features of 2 mammals. Bats are flying mammals, shrews are ground-living mammals. We got the mean body mass and the mean lung volume of both the bat and the shrew given in this table. Calculate how many times the lung volume per unit body mass of the bat is greater than that of the shrew. Give your answer to an appropriate number of significant figures. You're going to go 2 or 3 minimum. Give one suggestion to explain this difference. Okay, I'm not interested in that bit. I'm only doing the first 2 marks because this is a maths video. So calculate how many times the lung volume per unit body mass of the bat is greater than the shrew. So let's check it out. First of all, we need to work out what is the lung volume per unit body mass of the bat. So we're looking at really how many centimeter cubed per kilogram of bat. So I need to turn 0.09. So I've got 0.96 kilograms, and we need to find out how many centimeter cubed of lungs are in each kilo. So we're going to do 12.48 divided by 0.096, and that gives us 130 centimeter lung volume per kilogram of bat. Now we need to work out for the shrew how many centimeters cubed per kilogram of bat. So we need to do 0.72 centimeter cubed over 0.024 kilograms, and then see what we get. We get 30 centimeter cubed per kilogram of the bat. Now, how many times bigger is the bats than the shrews? Dead easy. 130 divided by 30. So that's for the bat, the 130. The shrew's lung volume per mass is 30. So we go 130 divided by 30, and we get 4.3. Hold on a minute. B. And it's 4.3 times bigger because we're going to two significant figures, really. So there we go. 2SF in biology is what they like if they're bussing out significant figures. All right, and yet another table, and another one. Right, table 4 shows the scientist results. Mass of protein, percentage of control. Mass of chlorophyll, percentage of control. So what we got here is we've got the mass of the protein as a percentage of the control is 40. The mass of chlorophyll, percentage of the control is 10. Do we need to understand what this question is going on about? No, it's just maths. The ratio of the protein to chlorophyll in control plants is 9:1. Use the information in table 4 to calculate the ratio of protein to chlorine in iron deficient plants. So the normal ratio is 9:1. So 9 grams of protein for every 1 gram of chlorophyll is what you would have in a normal plant. However, this table shows the results for an iron deficient plant, and we can see that it's saying it has 40% the normal protein level and 10% the normal chlorophyll level. So all you got to do here is say to yourself, well, I know that in the control there would be 9 grams of protein for every 1 gram of chlorophyll, but in this iron deficient plant there's only 40% of the protein. So we really want to do sort of zero point 0.4 times 9, or you could do 40 over 100 times 9. You want to multiply 9 by the 40% to find out what's 40% of 9, and then we need to find out what's 10% of 1 gram. And so that's what we need to do. So we're going to do 0.4 times 9 is 3.6, and 0.1 times 1 is 0.1. And now it asks for it in a ratio. What's the ratio of protein to chlorophyll now in the iron deficient plant? And what we do is we divide them both by the smallest to simplify the ratio, and we get 36 to 1. So there's 36 times more protein than chlorophyll in the iron deficient plant. There we go. 2 marks. Boom. Okay, figure 7 shows the mean distance between centromeres and poles at the end of the spindle during mitosis. We've got the mean distance between centromeres at the top, time in seconds at the bottom. Calculate the rate of movement of centromeres during the E phase. Give your answer in micrometers per minute and to 3 decimal places. So speed, time, yeah. When I think of rate, I always think of speed. And of course, you need time when calculating speed. It's distance over time. So when you think of rate, always think time. You're dividing something by time. Doesn't really matter what you're dividing. We need to give our answer in micrometers per minute. Micrometers per minute. And we need to do it to 3 decimal places. God, I'm losing my train of thought here. Right, so what I want to do is mark out E. E is from this line here to the end of the graph, okay? And if you read across the axis, it's like 1,750 to 2,500. So that's going to give us... Hold on a minute. I think I need a little correction here. So that isn't 1,750. If I add that up there and I go from there to there, that is 2,500 and that is 1,800. Made a little mistake there. That black line is just over that section. Okay, so we got a slight difference here. Our time is 700 seconds. Now, we're going to divide the distance by 700 seconds. So what is the distance? Well, 4 micrometers across there. And if we follow up to that line, it's just that circle I've drawn there. It's just below 20, so 19. So that's a total of 15 micrometers is the distance. And the time is 700 seconds. So we need to turn seconds into minutes because it wants the answer per minute, not per second. So we're actually dealing with 11.66 recurring minutes. And so we're going to divide distance by minutes. So we're looking at 15 or micrometers divided by 11.66 minutes. And equals 1.285714 micrometers per minute. Okay, I've used a diagonal line. You can just write minute to the -1. It wants 3 decimal places. So as I go 1.285, the 5 is greater. So I'm going to raise it up to 1.286. There we go. Okay, pause the video, have a go at these, obviously, before unpausing. So we got mice in group H injected with 2 milligrams per kilogram of monoclonal antibody in a solution of 500 milligram per decimeter. Calculate the volume of antibody solution the scientists would have injected into a 23-gram mouse. Give your answer in decimeter cubed and in standard form. Okay, this is the equation you should know off by heart from GCSE chemistry. Mass over concentration times volume. Actually, our mass is probably better to be in milligrams here, not micrograms. So obviously here, if I want to work out V, which is what I'm trying to work out in this triangle, I need to have M and C. And I don't have the mass at the moment of antibody. I don't have that mass yet. So what I need to do is work out the mass. And I've been given that we have a 23-gram mouse. But what mass do I need to give to the 23-gram mouse? Well, it's 2 milligrams per kilo of mouse. So I need to go divide 23 by 1,000 and then times it by 2 milligrams. So 2 times 23 over 1,000. And that gives me the mass of monoclonal antibody that we're giving to the mouse. And so that gives me M. So you need to do 23 over 1,000 times 2. And that's going to give us 0.046. And that's mg. So I'm going to have 0.046 milligrams, and that is my mass. So you might have got confused here and used 23 grams of mouse as the mass, but we're really looking at the mass of antibody that's being mixed in the solution. Now, we know the volume of the solution, we know the concentration, sorry, of the solution is 500 milligrams per decimeter. So all I've got to now do is 0.046, as that is my mass, and I've got to divide that by my concentration C, which is 500, which is the volume. And that's going to give me 9.2 times 10 to the minus 5. And that is the volume that we need. And there we go. And it's in standard form. Lovely. Let's move on to the next question. Okay, for this question, during the investigation, the scientists measured the size of the population of bacterial cells. Figure 11 shows the scientists' results. So we've got a line graph here with size of population and time in hours at the bottom. The generation time for a population of bacteria is the time taken for all the bacteria to divide once by binary fission. Use figure 11 and the following equation to calculate the generation time for this population of bacteria. Give your answer in hours. So this is quite a confusing one. Number of generations is log. We need to do the log of the size of the population at plus 4 hours divided by the size of the population at minus 4 hours divided by log 2. So what we're going to do first of all is find out what the size of the population is at plus 4 hours. And you see I've circled 4 on the timeline on the graph, and it's 3 times 10 to the 9. You've got to know how to read the graph. It says 10 to the 9 on the y-axis, but it's 3 squares up, so it's 3 times 10 to the 9. And just like that, down below at minus 4 hours, it's 4 squares up from 10 to the 6, so it's 4 times 10 to the 6. So my size of pop at plus 4 and minus 4 is 3 times 10 to the 9 and 4 times 10 to the 6. Got to log 10 that. You just need to press the log button on your calculator, then put brackets, put that in, and then divide by log, and then press 2. You don't need to worry about the 10. Your calculator will be set to log 10. Now, if you want to be uber careful, you can do it all separately. So you can do 3 times 10 to the 9 divided by 4 times 10 to the 6. You're going to get 750. So you then put that in brackets. You then just need to press log 750. When you press log in your calculator, a little open bracket comes up. Put 750, press equals, and then you're going to get 2.87. And you still need to divide that by log 2. So just press 2.875, divide by log, and then press 2 and equals, just to show you how to do that. And then you're going to get 9.55. Now, this was the number of generations, and this is our first mark. What a lot of work for 1 mark with this question. But that 9.55 gives you the number of generations of bacteria. What we were told up here is the generation time is the time taken for the bacteria to divide once. Well, we've had 9.55 generations, so they've divided 9.55 times. They've got 9.55 times. So we need to do the time divided by 9.55. So how long have we looked at on this graph? Look at the x-axis. We've gone from minus 4, right, to plus 4. So how many hours is that? That's 8 hours of time for this bacterial population to divide 9.55 times. So how much did one division take? Well, it would be 8 hours divided by 9.55, and this will give us the time for one division. One set of binary fission, and it's 0.8376, and that is hours. So that is the generation time. And then you might want to round that to 3 decimal places or 2 decimal places, so 0.84, or 2 significant figures, 0.84 hours. There we go. Hope you've enjoyed. What we're going to do now is finish the video. Make sure you subscribe, share and like for plenty more of these maths biology videos. Let's get to the marks.
You're still here? It's over.